I got interested in artificial intelligence when I was, I guess, teenager, but 21 Pilots did not exist then yet. But actually, the original interest, I think, was more in how to augment natural intelligence, and, well, doing better at Math Olympiads is just one aspect of that. There are so many others where you would think that it would be great if we could improve our mental states. You don't necessarily have to be a patient, like in psychiatry or whatever. So any one of us would like to get calmer, less anxious, to kind of think more efficiently, to have better memory. And if only technology could somehow detect our mental states and hopefully give us some feedback and somehow help with that, that would be great. That could be applied to both healthcare and to everyday life. But this is kind of a vision, a dream for like augmented human intelligence. And the road there seemed to be in exploring both how the brain works and how artificial intelligence can be developed to help us to make brain work better. So that is why I called my talk today Brain and AI. And I was planning to cover various aspects of my research in collaboration with many, many people within IBM, Watson, and other universities and other companies over past 10 years, and give you some examples where, on one hand, you focus on brain and on applications to field that's called computational psychiatry. I'll talk about that a little bit later. And you use machine learning and artificial intelligence techniques to analyze various data from brain imaging and beyond. On the other hand, you can draw inspirations from neuroscience and try to come up with better machine learning algorithms. That is why the arrow between brain and AI goes both ways. And since I usually tend to run late whenever I give a talk, I decided to put the acknowledgement slide first, because this work is done with many, many collaborators, as I mentioned, not only from the IBM Watson research, but also from other companies, universities. And all this wouldn't be possible without our great summer interns and postdocs and my colleagues in computational neuroscience and neuroimaging group. And I'm currently in AI Foundations group, but we all work closely together. So as I mentioned, I'll talk about this bidirectional arrow, and the first part of the talk will go from AI to brain and give some examples of how machine learning can help you analyze brain data and how it can help you to discover what's important for neuroscientists, so-called statistical biomarkers of certain disorders, for example, of schizophrenia, chronic pain, and so on and so forth. And the second part of my talk, hopefully I will not run out of time as usual, will be about the brain-inspired algorithms, and I give some examples where inspirations from neuroscience can give you better ideas about developing more adaptive and flexible AI techniques. So I ran into this paper relatively recently, but the quote from it, I think, describes the situation in the field of psychiatry quite nicely. I really liked it. It was a survey paper by Vieki, Poland, and Frank in 2015, which started, the first paragraph started like that. Imagine you go to a doctor and complain about chest pain, which was bothering you for a while. Doctor listens to you, listens to the description of symptoms and say, well, let's try some medication to lower your blood pressure, just in case you have heart disease. Week later or 2 weeks later, didn't really help. Let's try something against acid reflux. Oh, this helped, wonderful. Can you imagine this scenario in any kind of medical field? You would probably first take electrocardiogram or blood test or something like that. And yet in psychiatry, that kind of closely describes what is pretty much going on even now in like 21st century, with everything being much more computerized and with tests being developed for various disorders. In psychiatry, we're still kind of following the old traditions because it's kind of a complicated organ and it's not so easy to get objective measurements. But nevertheless, you would like to get closer to other fields where you can do blood test and EKG, something along the lines of objective measurements about the brain states. And hopefully some kind of, if not automated, but at least semi-automated diagnosis besides just a subjective evaluation by a particular psychologist or psychiatrist, which can totally differ from evaluation given by another psychologist and psychiatrist. Well, that is why there is now a growing, very popular field at the intersection of neuroscience, psychology, and computer science called computational psychiatry. And that's the name of one of our research groups in TG Watson. And the ultimate goal, as I mentioned, is to come up with techniques for extracting objective measurements from brain imaging data and from other possibly cheaper measurements, such as speech, text, video, and so on and so forth, perhaps wearable devices, to actually detect and monitor changes in mental states. The data, as I mentioned, can be classical, traditional, medical, MRI scanner, which gives you structure in the brain, functional MRI, which is so-called MRI movies that I'm going to talk about, showing how the brain activity changes during particular task or in response to some stimulus. Definitely EEG, electroencephalogram, it has certain pluses and minuses as compared to functional MRI, and so on and so forth. And the most interesting latest development in the field is that people started looking beyond the scanner and trying to tease out the signal about mental states from relatively easily collected data. As I mentioned, text, speech, video, wearables, you name it. So you don't have to put the person in the scanner in order to try and guess what's going on in the person's brain. Well, definitely, as I mentioned, it goes beyond psychiatry and can be quite useful for all of us, not necessarily patients, because you can think about tracking your levels of stress and anxiety using wearables, providing biofeedback. You can think about improving safety on our roads. There are multiple cases in the news the past several years where crashes at the New York Railroad happened due to a driver falling asleep because of sleep apnea, because being too tired, if only there was some kind of a device that could monitor the state of alertness and immediately kind of alert the operator or the driver or somehow prevent this accident in real time, that would be great. And going beyond health and well-being, of course, it's very interesting to, for many companies to track the mental state of people watching different commercials, watching different movies, listening to music, just to see how those stimuli affect mental states and whether particular movies may be more engaging than others and so on and so forth. So this is a whole field called neuroeconomics and neuromarketing, which tries to kind of detect and evaluate mental state changes while providing people with, say, advertisement to choose a better one, and so on and so forth. But let's start with classical way of measuring brain activity, brain imaging, and particularly functional MRI and EEG. So I'll try to give you a few examples of where machine learning and statistics applied to this type of data can be actually quite useful and can achieve quite interesting and accurate results in terms of guessing brain states and their changes. And I will only give a few examples from our own work, but this field is huge. And of course, I was a bit subjective when choosing the examples, but I think they will make the point. So you can think about trying different machine learning methods, for example, classifiers and regression approaches on functional MRI or EEG data in order to predict whether the person or detect whether the person, for example, is a control or belongs to a cohort of patients. And while you do that, we're actually quite surprised that you can sometimes do it very accurately. You can achieve up to like 93% accuracy discriminating between controls in schizophrenic patients based on functional MRI data. You can also track changes in cognitive states during video game playing. You can actually quite accurately evaluate the level of pain a person is experiencing. You would think it's very subjective feeling, but up to like 0.8 accuracy in terms of correlation between your prediction and the actual pain experienced. And so on and so forth. We kind of tried various types of data from subjects with cocaine addiction, and we found very interesting differences in their brain networks as compared to controls. And finally, of course, with the rise of deep learning, we explored how deep learning can help in this type of applications. And there are advantages and disadvantages because medical, biological fields like that don't usually have millions and millions data points. Therefore, deep learning should be used with caution. But when you add enough constraints on the model, it actually can provide quite a boost to your classification accuracy. We were kind of exploring mental load detection in healthy people, and deep nets provided best results as compared to off-the-shelf classifiers. So let me just quickly describe what the functional MRI data are about. So you're probably all familiar with usual magnetic resonance imaging. So you put a person in a scanner and usually just take an image, and that's commonly used to detect, say, abnormalities or cancer and so on. But the functional MRI is different because you actually collect not the image, but a sequence of images. Essentially, what you measure is indirectly related to true brain activity. You measure blood oxygen level dependent signal. Basically, if a certain part of the brain is more active, there will be more blood flowing there and more oxygen will be detected. But without going into details, the data you obtain look like 3D movies. Basically, you have a 3D image of the brain where instead of pixels in the image, you have voxels. It's 3D units. They're usually quite large. As I said, it's 3 by 3 by 3 millimeters or so. So there are millions and millions of neurons within one voxel. That's why I'm saying that we're measuring somewhat indirectly kind of brain activity. It's not neuron firings, but kind of the consequences of that. And then you have time points, usually at the order of like 1 to 2 seconds between them. And you get this sequence of fragments, which very loosely can be called brain movie. So the challenge here is you have extremely high dimensional data. You have anything from 10,000 to 100,000 voxels. Think about them as variables because their activity changes, and you have those thousands and thousands of time series. But you only have perhaps a few hundred samples. So it's a classical case in statistics and machine learning when dimensionality is huge, but the number of data points is relatively small, and you need to use special techniques to avoid overfitting and to make sure that your model can generalize to unseen data well. So what people usually ask about such data in the field, in neuroimaging, typically the question is, if the stimulus is given or task, can I find which brain areas are most relevant to this stimulus or to this task? And the most classical approach, which is much simpler than any of machine learning techniques, people in brain imaging just use standard tools, which are kind of univariate. You look at the time series of each voxel, you correlate it with stimulus. If it correlates high enough, you show that voxel, and you end up with areas on a brain map that are supposedly most relevant to that phenomenon. But of course, this is a very simplistic approach. From statistical perspective, you completely ignore correlations between brain voxels, and brain voxels do not act independently, obviously. So this assumption is very oversimplified. And therefore, machine learning comes in and tries to build instead multivariate models that take into account that the brain works kind of jointly, not independently. And you try to build predictive models using those multivariate techniques, and then also look back at what made them so predictive. And with this type of techniques, as I mentioned, you can try to detect changes in cognitive state. Is a person listening to a sentence or looking at a picture? Emotional states, is a person experiencing anxiety, or is a person happy, or is a person experiencing higher or lower level of pain? And also you can look at the differences between how the brain data look for controls in people with certain disorders, ranging from schizophrenia to ADHD, addiction, and so on and so forth. So as machine learning people, we usually tend to focus on classification accuracy or prediction accuracy of regression models. On the right side of this picture, how accurately can we classify? But that's not the final goal in this field, because you would like to get back to a neuroscientist or a doctor and explain what made your model so predictive. So interpretability is a key, and even more important than prediction accuracy. Prediction accuracy simply serves as a sanity check that your model does something reasonable. But the focus is, what are those patterns that the method could extract in order to make accurate prediction? That's why those statistical biomarkers or possible kind of patterns in the middle are the main focus of our machine learning applied to neuroscience. And there are various ways to go about this feature extraction, from the most straightforward, so-called sparse methods that we tried a lot on various data sets, and I'll briefly mention what they're about. But essentially, you try to build regression model while at the same time you try to choose the most informative subset of variables, say voxels. Then you can show a map to a neuroscientist and say, well, it looks like those areas are most predictive about your stimulus or your phenomenon of interest. The next step is when this is not enough, but you have lots of expert knowledge about certain disorders. Say schizophrenia is one good example. You know it's a network disease. I'll talk about that in a few minutes in more detail. That gives you ideas how to construct features rather than just use raw data. And it does happen that using network properties extracted from functional data can be much more accurate than using the raw data or standard approaches that people use in the field. And finally, the modern state of art in machine learning is learning representations. More generally, not necessarily just with deep networks, with any kind of hidden variable model that starts with raw data and tries to build hidden variables or features, perhaps in multiple layers, so that those features will be most predictive about some phenomenon of interest. So this automated feature extraction, I think in combination with some feature engineering, is perhaps the most promising direction in this field and many others. Okay, just to give you a brief idea, going one step back to the how do you build predictive model from fMRI data. The simplest case. Imagine you have Y, the stimulus or response, for example, a level of pain in a person, and you have the matrix A where each row corresponds to a time point and each column corresponds to the voxel activity. So you have very fat matrix with small number of rows, large number of columns, and you would like to just solve simple regression problem, linear regression. Unfortunately, you cannot just do it with such matrices. You need to regularize. You need to add constraints. Otherwise, you cannot solve the problem, and what you get probably would not generalize well. So you want to kill two birds at the same time, improve generalization, and also find interpretable solutions. And the type of methods that people use for these problems is called sparse models, sparse regression, sparse networks, and so on and so forth, which are all based essentially on fitting a model where many coefficients will be forced to zero. There is a particular way of doing that using L1 regularizers, but I'm not going to go into technical details right now. So using such methods kills two birds at the same time, provides you, say, brain maps where only the most important voxels light up, while at the same time, hopefully achieving highly predictive accuracy. So this is a classical example of such problem. Just because it's an old data set, and we collaborated with our colleagues from Northwestern University on kind of several types of analysis of this data. So imagine, like at university, you have a freedom to use your graduate students as subjects and inflict pain on them in various ways. Probably less painful way, they don't have to take any tests here. They only have to endure some thermal pain. Mental patch is placed on their back, and it's kind of heated sometimes. I mean, don't worry, it's not terribly high temperature, but it gets uncomfortable. And 14 graduate students have to rank their pain on the right. So as they experience it, they have to just draw this continuous time series and tell us how much pain they feel. The interesting thing, if you look at the time series on the right, there is lots of intersubject variability. There are quite sensitive people there, and there are a few tough guys. As it turns out, there are some reasons for this difference between being tough and sensitive, and that's a good point to show to those supposedly tough guys. They might just have different pain threshold. So the question is, can you possibly look at this time series and predict them accurately from the brain movie, from functional MRI? And to our surprise, and to surprise of our colleagues, actually for quite a few people, you can quite accurately do that. You would think that it's very subjective feeling of pain, but by looking at the brain imaging data, you can, by using those methods from sparse regression that I mentioned, there is classical lasso, there is augmentation of that to elastic net, there is group lasso, there is fused lasso, and so on and so forth. There are various kind of combinations of regularizers. You can get quite accurate results. You can also identify subsets of voxels in the brain that are most involved in this prediction. And you can also play with stability of your models, again, some technical details, by using additional regularizers on top of sparse models. So bottom line seems to be quite a useful tool for this type of a problem. But as I mentioned, there is this intersubject variability, which sparse regression models do not seem to capture, but dynamical models, basically second-order differential equations, can capture those. Again, quite surprisingly, thanks to my colleagues both at IBM and Northwestern, we developed this very simple dynamical model with only 3 parameters, which can actually fit temperature to pain perception, not yet looking at the brain data. And the reason for all those tough guys being so tough was perhaps that their pain thresholds were just too high. So every person could be fit to kind of this model, and essentially you get, instead of a fingerprint, a brain print with the 3 parameters: pain threshold, forgetting, and anticipation. And that quite accurately nailed down all this intersubject variability. And of course, combining analytical model with a data-driven model in a particular way, such as you don't know the stimulus, you may not know what's causing pain, but you can predict that stimulus from your brain data, and then you can use your dynamical model to make the link between stimulus and behavior, perception. The overall model, to make the long story short, was considerably more accurate than just the data-driven model. So that was a good example and a good lesson for this field, that machine learning is great, but sometimes it can really benefit from domain knowledge and from analytical approaches. So my next example, I'm switching from variable selection to, or feature selection to feature construction. And that was an example of schizophrenia where we're, again, quite amazed at just how accurate the prediction could get when proper features are used. And when I say proper features, we looked at the data where schizophrenic and control patients were doing the same task in the scanner. And when we used standard activation features, what people use in the field, pretty much how the voxels in the brain correlate with the task, we didn't see any statistically significant differences. Essentially, the patients responded to the task in pretty much same way as controls did. But if you actually look at the so-called functional network, if you look at the correlation matrix across all the voxels in the brain, and look, you can threshold it, you get a graph. You threshold the correlations, and whatever remains will be the links in your graph. You can look at the degrees of nodes, how many connections they have. You can look at the actual weight of those connections, and so on and so forth. They are very powerful, informative features that can distinguish between controls and patients with up to 93% accuracy in this particular study, while standard activations, response to task, were close to chance. So the take-home lesson here was that sometimes a schizophrenic brain can respond to the task very similarly to control, but there is a lot more going on in that brain in terms of how the network is working and how different areas interact with each other, which might be quite different, and that you need to exploit in your approach. Moreover, a more recent paper, which just was published in April in NPJ Schizophrenia, it was another study with our colleagues from University of Alberta on much larger data set, publicly available, where we went beyond just classification and tried to do symptom severity prediction. This was much more challenging data set from multiple sites. There is much higher level of noise just due to using different fMRI scanners. And the cohort of patients was much more heterogeneous. Nevertheless, we were able to achieve like 74% accuracy across those multiple sites. We also found the network features to be quite discriminative. And furthermore, they were also somewhat predictive about symptoms, like inattentiveness, well, attention or lack of it, severity of bizarre behavior, and so on. So this is very interesting because this is even more clinically relevant than just discriminating between patients and controls. Okay, so I guess I probably need to speed up a little bit. How much time do I have? 5 minutes. Oh my. Okay, so I'll have to really go quickly over that. But another kind of success story was trying to use machine learning to answer the question whether certain drugs, such as methylphenidate, also known as Ritalin, can actually normalize brain activity in cocaine subjects. And the reasons for this question were that actually Ritalin or methylphenidate is chemically very similar to cocaine and acts very similar to cocaine. You'll be surprised, you give it to people with ADD, right? So yes, the difference is that cocaine has a spike in dopamine. It basically blocks the dopamine transporters. Actually, the MPH does the same thing, but much slower. The half-life of cocaine is 20 minutes. And with those Ritalin and basically drugs, you get like 90 minutes. Much slower. You don't experience high. Supposedly, you don't get addicted. Other than that, the idea was, again, working with our colleagues from Mount Sinai, to test whether using kind of drug to fight the drug is a good idea. And it's being done like with nicotine patch and other type of medications, depending on what you're addicted to. While we're not claiming it's going to really treat cocaine addiction, it was interesting to observe that when you look at the functional networks of the brain, when cocaine addicts take MPH, they become much more similar or harder to discriminate. That's what classification accuracy shows here. The classification discrimination accuracy between them and controls goes down. They look more normal. Doesn't mean that necessarily you can use it as a treatment choice, but it was kind of machine learning's 2 cents towards exploring this question. And finally, I definitely have to talk about deep learning whenever I talk about modern AI. And while, as I said, you need to use it with caution in the data sets with small number of samples, or relatively small number of samples. Nevertheless, it seemed to be quite helpful if you use enough regularization or constraints on top of them. The example of the study was, well, healthy controls. We're just studying their levels of memory load. People are asked to look at certain number of symbols from 2 to 8, remember them, It's harder to remember 8 than 2. And then when a symbol is shown, they should tell us whether they saw it before or not. So you have several levels of mental load, and you try to see whether you can actually predict the current mental load or detect it from EEG movies. The technical details here was that we actually not just used EEG time series, but we mapped them to their spatial locations in the brain. So we made images where color corresponded to frequencies, location was a projection from the brain, and then the several frames corresponded to the particular trial. So you get those movies, and you apply certain deep learning techniques, you actually can get quite predictive results. To make long story short, again, the most successful approach turned out to be actually recurrent convolutional networks because they used time aspect together with a space aspect. And next important point in this study was not only you want deep learning to help you with classification accuracy, we reached like up to 91, about like 10% more than the off-the-shelf classifiers. The question was, can you make deep learning interpretable? And that's another challenge with deep learning in these applications. So here particularly we used so-called deconvolution approach, and we're able to map the features we learned back to brain in order to understand what they mean. But in general, the focus of deep learning is not so much on interpretability. And I'm just trying to kind of, once again, focus on interpretability here. Therefore, whenever you use deep learning in brain imaging, you better have some method of mapping back the features you constructed to the brain. Okay, so just to finish this part of my talk, and there is a second one, a few lessons that we learned, as I mentioned. The feature engineering here is still important. You need domain knowledge, say schizophrenia is network disease rather than area disease. And those probably are not likely to be completely replaced by automated deep learning. They better be combined with that rather than replaced. Interpretability is very important here, no matter which method you use. And combination of your machine learning approaches with analytical models, especially dynamical models, can really provide a boost to your accuracy. So, as I mentioned, deep learning has to really pay attention to first interpretability, and second, to how to deal with the moderate-sized data sets. We only had a few thousand samples, not millions and millions. You need to regularize properly with dropout and other constraints, but you need to make sure that effective complexity of the model will match your number of samples, the sample complexity. And very briefly, if I have just a few minutes, I think I'm probably -5 or -10 by now. Yeah, I just wanted to mention that there is lots of interesting work going on beyond the scanner, where you may want to use different variables and ask the question if they can provide you with any data useful about detecting mental states. So we played with a variable EEG device, which is really cheap, a few $100s, and only has 4 electrodes. So you would ask, what kind of mental states can you possibly detect with that? But surprisingly, though it's a very small study, disclaimer, it's like 16 people only. We just tried it on our colleagues at IBM. But apparently, if you collect those data while giving people different videos to watch, you can distinguish and tell them that actually right now you're watching more of an emotional movie, funny cat video on YouTube, or you're watching educational Khan Academy video. And all that you can do by extracting proper features from this simple variable EEG device. So I just wanted to mention that you can actually get 74% accuracy even with this kind of very cheap data. That was interesting. And the most interesting part is the research, ongoing research in our group. Well, it's mainly led by my colleague, Guillermo Cecchi, and his postdocs. Amazing results that you can achieve by using transcribed text from interviews with patients in order to discriminate between patient and control. Just by looking at transcribed interviews with prodromal patients who did not yet develop schizophrenic episodes, psychotic episodes, you can pretty much almost with 100% accuracy predict who's going to develop an episode 1 or 2 years from now. Again, disclaimer is it's a relatively small study, about 30 people, was published in NPG Schizophrenia 2 years ago. And there are many other publications along those lines. You can find them online if you just Google our publications on distinguishing between controls and people taking ecstasy. You simply measure semantic distance from what they're saying towards like love and friendship. And quite accurately, you can tell who is on the drug, so on and so forth. Measuring coherence is one of the important features here, which helped with classifying schizophrenic patients. And I'm not going to go into slides on that, but you can definitely measure coherence of many political speeches and kind of compare different political figures in terms of coherence of the speech and find very interesting results, but I'm not going to call any names here. You can guess what kind of plots we got with certain speeches of certain people. Yeah, so pretty much as expected. So overall view, where we would try to get in the future, would be to use those relatively cheap variable speech, video, text data to try to monitor mental state of people, not necessarily patients, as I mentioned. They could try to help you in real life to maybe prevent you from losing attention while driving, or maybe detecting the change in your mental state based on the words you're using and trying to alarm your friends that maybe you're kind of developing a depressive episode and they should kind of check on you. Or when you're getting too nervous before you talk, maybe to remind you to just calm down, it's just another talk, who cares? And so on and so forth. So if you've seen the movie Her about the personal assistant, it was a really nice movie. If you didn't, I really recommend it. Something along those lines would be great, although the later development of this movie into romantic comedy is not necessary. It's not included in that slide. And finally, since I'm totally running out of time, I just wanted to mention that there is lots of work underway at the intersection of our AI Foundations group and the computational psychiatry and neuroscience at how to use inspirations from how brain works in order to develop better machine learning algorithms. And there are a couple of recent papers at HCI conference, which are going to be in Australia next month. One of them about neurogenetic adaptive dictionary learning, where we use inspiration about adult neurogenesis, very interesting phenomenon, but I don't have much time to talk about that, on how to come up with adaptive representation learning methods where the hidden variables or features constructed will be expanded and compressed as you go, especially in response to non-stationary data. Because we know from neuroscience that neurogenesis is most pronounced when people or mammals exposed to changing, rich, challenging environment. If you do the same thing with a computer program, when you use adaptation, you definitely seem to be getting much better performance than when you don't. And that kind of confirms neuroscientific observations and gives you a better machine learning algorithm. So, thank you very much. I will, I guess, stop here.
Thank you, Rish.